Welcome to this video where we're going to build a simple RAG pipeline for data retrieval using AI. If you're building a RAG application or any AI application in general, you know that there's probably tons of different pieces you need to put together. Things like how you load and split your documents, which embedding models to use, and what kind of database you want to store things in, and of course the LLM model itself. With new options always coming out, it's really important to be able to modify different parts of your application easily. And not just that, but also evaluate it against benchmark so that you can see whether or not those changes made it better or worse. Today, we're going to do this by building a really simple modular pipeline in Python. We have some PDFs with completely made up information about a fictional town called Swan Lagoon. Our application will use this to answer questions. We'll be able to query it directly with a CLI command. We'll also have a command to run a separate evaluation test against a set of benchmark questions and give us a total score. The goal here is to create a setup where you can easily swap out different components of this pipeline and, more importantly, test how it performs. First, I'll show you how to set up the basic structure of the pipeline. Then, we'll run an initial evaluation against this pipeline to test its performance. After that, I'll show you how easy it is to upgrade a component by switching it to use a better algorithm. And then we'll rerun the pipeline again to see how that change will impact or improve the results. This way, you can quickly try out different ideas and see what works best. Now for this video, I will assume you're at least a little bit familiar with how RAG, or Retrieval Augmented Generation, works. If not, then you can check out some of my other previous videos about it. And because I want to focus on how everything fits together at a high level, I won't be spending too much time on the code itself for this project. However, the code is all available on GitHub if you wanted to have a closer look. The links are in the description. All right, let's get started. Before we dive into the code, let's first take a look at the architecture. At its core, a RAG pipeline is designed to take your own documents, PDFs, Excel sheets, whatever you want, and then use them to help an LLM give you better, more accurate answers to your questions. Our pipeline is made up of a few key parts that work together to achieve this. First, we have the indexer. This is what will read your raw documents. Documents can be long, so the indexer's job is to split them into smaller pieces, which we will call chunks, and then it gets them ready to be stored. Next is the data store, or the database. This is where all of those processed document chunks will live. Along with the text of the chunks itself, we will also store something called embeddings, which are basically numerical arrays that represent the text. This is what we'll later use to query for the right chunk or the related chunk, given a certain thing that we want to look for. We'll also need an AI model to generate these embeddings, and this will need to be the same model we will use for the query later on as well. And when you want to ask a question, the retriever is what we'll use. It takes your question, it converts it using the AI model into an embedding, and then you'll use that embedding to search the data store. The goal is to find the most relevant document chunk that might contain the answer to your question. Once the retriever has found the relevant chunks, this could be 5, 10, 100 of them, the response generator will take all of these and then combine it with your original question and feed all of that information to the LLM. The LLM then uses this context to generate the final answer. Finally, we have the evaluator. Now, this is not technically a part of the RAG application, but it's a very important part of the pipeline because this will help us achieve our goal of trying out different components and then checking whether or not the pipeline has improved as a whole. What the evaluator will do is that it will basically take in a set of questions that we have prepared an answer for, and then it's going to run that using the current indexer, data store, whatever we have, the whole pipeline, and it will give it a final score. And this will let us basically test the whole thing against the same set of information and get a result that we can compare. Now, there's many frameworks and designs out there for building a RAG pipeline like this, but this basic structure is what they all usually boil down to. And in this project, we'll implement the interfaces for this ourselves using just basic Python, because the goal here is to learn how all of these pieces fit together. So now with the architecture in mind, we can go ahead and start setting up the project. We'll start with the data store. First, I recommend you going over to my GitHub and downloading or cloning the project if you haven't already. Next, you'll probably want to create or set up a Python virtual environment to install all of your dependencies for this project. Here's the command you can use to do that. Once the virtual environment is active, we can use this command to install all of the dependencies listed in the requirements.txt file. Now, this pipeline uses OpenAI for generating embeddings and responses, so you'll need to set up your OpenAI API key. You could do that by setting up an environment variable and then putting your key into that environment variable like this. Now, if you wanted to use a different AI model or a different API, you can probably swap it out quite easily. There's only 1 or 2 places where we actually call the model itself, so just go ahead and change those. The reason I start with OpenAI is just because it's a very common one, so it would just be an easy way to start. All right, so with the environment ready and set up, let's take a closer look at the data store component. Again, this is where we're going to store all of our document chunks and their vector embeddings so that we can query them later. Okay, so for this pipeline, the database we're going to use is called LanceDB. This is a vector database. It's a simple file-based database, and it's really easy to get it running locally, which makes it a good place to start with for this tutorial. You can find the implementation in the source/implementation/data store file. At the top there, we're defining the DB path, which is going to be the local path where the database file will be stored. In this case, it's going to be in the data/sample LanceDB folder. You'll see the file get created in your project when you run this. It also sets the name for the database table where our data will live. And this one, we're going to call it RAG table. And it also specifies the size for our vector embeddings. Now, every model will could generate different embedding sizes, so it's important to check the documentation and make sure that you know how many vector dimensions are being generated by your model. In this case, the OpenAI embedding model generates a vector dimension of 1536, so that's what we'll put for the vector dimensions. And finally, we'll have a function to load the table or create a new one if it doesn't already exist. The data we store in the LanceDB table needs to follow a specific structure or a schema. This is what will define what each entry in the database will hold. The schema we use will have 3 main fields. Vector, so this is going to be the vector embedding that we'll use for the text. The content is going to be the actual text of the content of the document chunk itself. So when we split our source document into pieces, this is going to be where that information lives. And then the source is going to store some metadata about where that content came from. So if we wanted a reference link that we could click and then it'll take us back to the original file or the page, this is where we can store that information. Now, I've just popped over to the project to show you this code in the editor itself. We've actually split up the components into 2 folders. One is for the interface, which just shows you the abstract class that we will implement to make this work. We actually have 3 methods. We have one to add a list of items, and this is a data item, which will have the content and the source. Another function to get the vector. So this could be any content, and we get the embedding using this function. And this is where we will plug in the AI model. And then finally, we have the search function, and this is one where we will use later on to fetch relevant chunks or entries from the data store. So we can search for a query and have a top K results return. And the reason we did all of these components as interface first is because that's the whole point of the pipeline, is that we want the pipeline to work with only just understanding the interface. We want them to be able to connect and wire up, and then we can implement each of these pieces any way we want as long as they conform to this interface. But our data store implementation itself is here. You can see the whole thing, and here you can actually see us using OpenAI's client to get the text embedding. So this is a very important part of how we both query the data store and how we create the original embeddings for the source material. Now that we have our data store set up, we'll go ahead and set up the rest of the core components. So that's going to be the indexer, the retriever, and the response generator. First up is going to be the indexer. This component takes our raw documents and then gets them into a format that our data store can understand and search for effectively. And this is some simplified code from what the original version of the indexer will look like. So this index method will take a list of file paths, it will loop through them, and then uses this helper function, which we've kind of omitted here just to make it simpler, and to break each of those documents into smaller pieces. And it'll create a data item for each of them. This is really basic. It literally just chops up the document based on how many characters per chunk that we want to chop up. And it's probably not a good way to split up the document. For example, some really important pieces of information can be split up into two pieces when we actually want them together in one piece, and it doesn't make sense. This is not a great way to actually do this, but it's fine because right now we're just focused on building out the pipeline, and we want to be able to test it later and then come back to upgrade it. The next component is the retriever. Its job is to look at the user's question and find the most relevant chunks in our data store. Our basic retriever setup is pretty straightforward. It just uses the search function that's already built into our database from the previous step. And the search method takes the question and how many results we want, and then it just asks the data store to do the searching. And remember, the data store itself has the ability to turn that original query into the vector for the search. And this one doesn't create the response or understands the response for us yet. It just takes, 3 items from the database or more if you want, and returns all of those results raw for the next step. And that next step is the response generator. It uses a helper function to invoke the AI model, which in our case is OpenAI, but you can actually switch that out with any LLM model that you want. It will take in the original query and the list of results that we found using the retriever. And the system prompt here is to use the provided context and provide an answer to the user's question. And we also have to tell it explicitly that if they can't find the answer within those sources that we provided with, to say that they cannot find that information and not to make up any information, because that's quite a common way for something like this to fail. Okay, so now that we've covered the basic ideas of those 3 components, let's take a look in our actual IDE and see how they look. So here in the interfaces folder, we have the indexer, which only has this index function. All it does is just, you just feed it documents, and it's supposed to do something and kind of just pass that off to the next step. So that's very basic. We have the retriever, also really basic as well. It just has a function to search for the query and return the most relevant items. And then the response generator, also really basic. Each of these are basically one method interfaces. The response generator will take the query, a list of result context from the previous step, and generate the actual final response that we want to send back to the user with. And the implementation itself, I know I did truncate it in those screenshots, but you can see the whole thing here. And it's pretty simple still. This one just indexes the document by splitting them into chunks of 200 characters. And the retriever also really simple. It doesn't really do anything more than these 10 lines of code. The response generator, we have the system prompt in here, and we also have this invoke AI function. And if you kind of just control click that, you can see that it just wraps an OpenAI client. And if you wanted to use something else, you wanted to use Claude or Google Gemini or your own model, this is what you'd change. Finally, with all of the core components set up, let's talk about the final piece of the pipeline, which is the evaluate. I really think that this is the highlight of the pipeline, because the whole idea for us having a pipeline is so that we can test the whole thing whenever we make a change and get a score at the end. Now, for me to explain how the evaluator works, let's first take a look at the source material that we've prepared. I've basically generated a set of 4 PDFs to feed to this pipeline. And this is all made up information. The reason that I did this is because when I'm evaluating the pipeline, I want to be able to test that it can recall information from these documents. So I made up a bunch of specific details that LLM models would just not know on their own. For example, I made up the name of this town. This is called Swan Lagoon, and the documents basically have a business directory. These are all fake businesses with phone numbers, opening hours, and addresses. And it's got a tourist guide with really specific information, like, for example, 231 meters or 3:38 p.m. Like, these are all really specific numbers and names. The point is that I want to just be able to test this benchmark accurately, but LLMs already have a lot of information. So if you use data sets that are real or that exist, you want to be able to separate whether it's actually being able to recall information from the data you've prepared from the source material, or it's just kind of remembered it from a past training. Now, what about the evaluation? So that's going to be in a separate folder under sample data called eval. And these are basically a list of questions and answers. And you can write these manually, or you can just get LLM to generate these as a one-off and then kind of fine-tune it yourself. But the point is that we just have questions and answers. Now, we can't test this like a typical unit test where everything's just mechanical, because when we actually run a query on the pipeline, we might get the right answer, but it might not be the right text, or it might not be exactly the same text. So for example, this one, it says, when did this mine close? And with the company that operated it, the answer is 1935. So anything that has this number in it is a good match. It doesn't have to be this exact answer. And you kind of get the idea, is that the answer given by the pipeline is not always going to match the string that we've provided it. And this is the problem that we want to solve with the evaluator. And the solution to this is pretty simple. We will basically just use AI as a judge to score whether each question is correct or not. It's not perfect, and yes, there will be some cases where it might actually give us a false positive or a false negative, but it's probably good enough, and it's probably the best we can do for now. And here's an example system prompt that will give to our LLM model to do the judging for us. And now let's jump over to the code editor to actually take a look at the evaluator. The interface is really simple. We have an evaluation result, which has the question, the response, expected answer, and a score, basically a true or false, whether it was correct. And sometimes we want to debug it, so we'll also have a reasoning field, so that if something's, we look at it and it doesn't give us the right answer, we can look in the reasoning. Why did the AI come to this decision? Our evaluate function is also quite simple. It just has the query, the response from the pipeline, and the expected answer. It's going to basically loop through our evaluation set and run this for each of the questions. Now the implementation, it's a little bit longer, but it's still pretty simple. The system prompt is here. It tells the LLM model to use XML tags to reason about the question, but also to return the results. And this is so that we can get both the reasoning and the result as part of the response. For the user prompt, we're just going to format it with the query, the question in the evaluation set. The query is going to be basically this part here, and the response, which is what we get from the pipeline, and then the expected answer, which we also have in the evaluation set. Then we basically plug in the system prompt, the user prompt, we get the response back, and the raw response will have this reasoning result tags. So we'll extract those tags, we'll parse it and get the results out, and then we'll parse the answer, whether it's true or false, because when the LLM answers us, it's all text. And this should work. If it doesn't, we can do some, error catching and maybe retry it, and hopefully you'll get the answer in the right format. But eventually we should get the response, and we'll just plug it into the evaluation result, and that is what we'll return. So now that we've got all of the individual pieces created, the data store, the indexer, the retriever, the response generator, and the evaluator, let's put them all together into a working pipeline. This is where we wire everything up and create a way to actually run it from the command line. We'll start by creating a central class called RAG pipeline. And this will hold instances of all of our components. And this is what the definition for the class looks like. And notice that it doesn't know about the implementation of each of these components, only the interface. We can plug in any class that extends from one of these interfaces. These are going to be the methods we have in the RAG pipeline itself. And these methods will simply call the corresponding methods on the component instances that it holds. For example, when we call add documents on the pipeline, it basically first uses the indexer to process the raw documents into chunks, and then tells the data store to store those results. So it's not really doing anything fancy. It's basically just connecting all the different pieces of our individual components so that they kind of flow. Now we probably want a simple way to use this pipeline. So what I'm going to do is create an arg parser so that we can run it from the command line. I'm just using Python's built-in argparse module to create a simple command line interface. And here's some of the code to start for setting up the argument parser. Back in the IDE, this is what the arg parser looks like here. We're basically just creating a flag for each of the functions that we want it to do. And we want to be able to run the whole thing. We want to also be able to just run specific pieces of the pipeline. For example, just adding a document or just evaluating or just querying the pipeline. Finally, we'll need a main entry point for the script. So that's just going to live in the main.py file. This file will use the parser we just created. It will also instantiate the RAG pipeline with each of our actual component implementations, and then it will call the right pipeline methods based on the command we give it. And finally, the main function just wraps it all together. We create the CLI parser, we create the pipeline using the function we just saw earlier, and we also allow the users to either specify the paths for the source files of the evaluation if they want, or we'll just use our default paths that we've hard-coded previously. Okay, so now that we have the pipeline built out at a very basic level, we can try running. When we first run the pipeline end-to-end, it's going to do three things. It will first reset the data store to make sure we start with a clean slate. Then it will add all of the documents from our source directory into the data store using the indexer component. And by default, that was the path that we specified in sample data/source. Finally, it will evaluate the entire pipeline's performance by using that set of evaluation questions that I showed you earlier. And again, if you want to see how all of this is connected, just go to the main.py file in the source code, and you'll see the function to create the pipeline and the main function that also runs it. And you can see here that we actually have these three distinct commands: reset, add documents, and evaluate. And if we specify the run command, it's going to do the pipeline end-to-end. So it's actually going to do all three of these steps one in a row. But if you actually just want to run one of these steps, or you want to just, for example, set up the pipeline and then query for a specific result, then you can use these sub-commands as well. With that all set up, let's head over to the terminal and run the command using Python main.py run. And you can see here it's doing the first step, which is resetting the database, and now it's adding the source documents. And now it's running the evaluation. And when the evaluation is finished, you can see the results. So here, the total score is only 10 out of 25, which is pretty bad, but we knew that because our indexer component isn't using the best strategy. But anyways, if you scroll up, you'll be able to see the results of the evaluation. For example, you could see this is one of the questions where it got correct. The answer was that the community library was open Monday to Friday and from this time to this time. And that was pretty much the same as the expected answer. So the rating here is good. But there's also a lot of examples where the answer was wrong. For example, here it says that the recycling is collected weekly on Mondays, but the real answer is that it's collected fortnightly. Or some of them where it couldn't even find the information. So it just says that I can't find that information. Okay, but this is basically how you can run the pipeline end-to-end and evaluate it. And if you're actually deploying this app, you probably want to just use it to ask any query you want. For example, if you've deployed it as a customer-facing app and you want to make it into a chatbot. So for that one, we actually use the query command for the pipeline. And here, I'm just going to query for the opening year of the Lagoon Breeze Hotel. And here, it's found the three most relevant results. And in those results, the opening year is specified, so it was able to answer us correctly that the hotel was open in 1962. Okay, so now we've seen how to set up a basic pipeline, how to run it against single queries, but also how to evaluate the pipeline as a whole against a set of results. Unfortunately, our evaluation results were pretty bad, so let's take a look and see if we can improve one of these components and then test the pipeline as a whole again to see if we can get a better score. Now, remember how our initial indexer just splits the PDFs into fixed size text chunks? It's a simple approach, but it really doesn't quite understand the structure or the meaning of the document. So it splits them, maybe it's too small, maybe it's too big, or it doesn't really get the right size. And it makes it hard for the retriever to find the best pieces of information to use. So to get the better quality data into our database, we're going to swap out this basic indexer for a more advanced one using a library called docling. And this is designed for exactly this purpose, like splitting documents, processing, and chunking them. It works with more than just PDFs as well. So this is the improvement that we're going to make to our system. Now, I'm going to go to GitHub and show you the commit that made this change. So you can see in this commit, let me just zoom in. First of all, we removed Py to PDF. We don't need that anymore. And we've replaced the dependency with docling. And this is in our requirements.txt file up here. And then we made changes to the indexer file itself as well. So you could take a look. This is pretty much just details, but the main point here is that we're replacing this fixed size chunk with a library that already has better logic on how to break apart documents. If you've cloned the latest version of the project, it should already have this, so you don't have to worry about this. But take a closer look at this if you want to know how it's done specifically. Now, after the change is made, you can just go back to the terminal and run the pipeline again end to end and see if the results are any better. And here are the results from the new evaluation. This time it's improved by a lot. It's now scoring 18 out of 25, and that's because it can fetch better quality results for each of these queries. Again, for any of them that it still gets wrong, you can actually scroll up and then look into the answer, the expected answer, and then the reasoning. And this is usually the feedback loop you can use to figure out, okay, well, what's the next improvement you can make? And there's a lot of improvements you can make to a RAG pipeline. I mean, we're only really just scratching the surface. Pretty much all of the components have more advanced versions that we can build from and different techniques and algorithms we can use to improve the results. So if you're interested to learn more about those or see those, then let me know. Okay, so to wrap up, I know we went through all of this quite quickly, but my main focus here was to really show you the core idea behind creating a RAG pipeline and show you how it can be a useful part of your workflow. The key takeaway here is that if we use well-defined interfaces for each of the major components, we can easily swap them out and test them. In this tutorial, we only modified the indexer, but as I mentioned, there are other ways to modify the components. We could try adding re-ranking. We can improve the response generator, for instance, to see how it improves the whole system. In reality, a highly advanced RAG pipeline will actually have quite complex databases, retrievers, and response generator components as well. And by having an evaluation system as part of our pipeline, we're really able to test any changes quickly and get a concrete score that we can compare. And if you wanted to take a RAG pipeline to production, you might not want to build your own. There are existing frameworks out there. I know of LangChain and Llama Index that I see kind of people use quite a lot. There's probably a lot more out there as well, but I haven't done enough research to discover all of them yet. So you could look into those as well if you wanted to use a framework to do this instead of kind of creating your own one. But if you did want to see the code for this, as I mentioned at the start, the code is on GitHub, links in the description. Otherwise, I hope this was useful, and I'll see you in the next one.